We're now going to talk about a type of equation that we can solve just by adding, subtracting, multiplying, and dividing the same thing from both sides of an equation. These equations are called linear equations, and we'll see why they're called linear equations a bit down the road. For the moment, we can just take this as a bit of definition, a bit of terminology. But let's get into exactly what it does mean for an equation to be a linear equation. And we're going to start by talking about expressions. A linear expression is an expression which can be written as ax plus b, where a and b are real numbers and x is a variable. A linear equation, then, is an equation where both expressions in the equation are linear. Let's see some examples. So 3x plus 2, this is a linear expression. And this is pretty easy to see. 3x plus 2 is precisely in the form ax plus b, where a is 3, b is 2, and x is x. Then we might have something like 1 minus x. This is also a linear expression. And this one, it's not written in precisely the form ax plus b, but we can rewrite it that way. So this is a linear expression because 1 minus x is equal to, we can use a little bit of rewriting things here. Remember that subtracting something is the same as adding the negative to it. So 1 plus negative x is the same thing as negative x plus 1, because the order of addition doesn't matter. And this equals negative 1 times x plus 1. Again, remember that if we've got a negative in front of something, that's the same as negative 1 times that thing. So 1 minus x is, in fact, a linear equation because it's the same thing as negative 1 times x plus 1. So here the a would be negative 1 and the b would be positive 1. So this is also a linear expression, even though we have to write it a little differently. Along similar lines, if we have 2 times 3 minus x plus 7, this is also a linear expression. This one we've got to expand out a little bit, simplify a little bit. So if we have 2 times 3 minus x plus 7, that's the same as if we distribute the 2, that's 6 minus 2x plus 7. And now if we rearrange things, we can put the negative 2x in front, and then the 6 and the 7 combine to equal 13. So the expression 2 times 3 minus x plus 7, we're still going to consider it a linear expression because it can be written in the form ax plus b. For a non-example, we can look at something like x squared plus 3x plus 2. This is a non-linear expression. There's no way to rearrange this or to rewrite this or to simplify this in such a way that will make it look like a times x plus b. Intuitively, what's going on here is that this x squared piece is what's making the expression nonlinear. In linear expressions, variables aren't being multiplied by any other variables. That's one way of understanding what a linear expression is. It's one where the variables are only being multiplied by other numbers. They're not being raised to powers. They're not going into square roots or into other functions, things like this. It's just the variable is sitting there, not being multiplied by anything else except a number. So when you see exponents other than 1 on a variable, that means that you are probably looking at a nonlinear expression, unless there's a lot of simplification involved. And then finally, we could take any of these linear expressions we've got and make a linear equation out of it. If we take two linear expressions, set them equal to one another, that's going to give us a linear equation. So this is what linear equations are. Let's talk about how we can solve them. And there's a general strategy that we've got that will always work, but I want to emphasize right away that this general strategy we have here will always work, but isn't always the best way of solving the problem. Sometimes there are more efficient ways of solving it that don't directly use this strategy in precisely the steps in the order that we're going to write down here. So you should really think of this as sort of a framework, inspiration for how to solve linear equations. So general strategy for solving linear equations. So let's say we've got a linear equation. Step 1 is we want to simplify both sides, if they aren't already. Now, this is just a good idea to do in general. In general, you should simplify both sides of an equation before you start doing anything else with it. Now, once we have simplified both sides, we're going to get something where you've got two simple linear expressions on either side. So step 2, we want to quote, gather all the variable terms on one side by adding or subtracting. A variable expression. Step 3, we're going to gather all constant terms on the other side, again by adding or subtracting. And then step 4, we're going to divide to get the variable by itself. So let's see an example right away, a simple example of how we will use this strategy. Let's say that we've got 5x minus 12 is equal to 2 times x minus 4. So here's our equation that we want to start with. So step 1, we'll simplify this equation. Now the left-hand side of this equation is simplified. Nothing else we're going to do with that. The right-hand side does need one step to simplify it. We're going to take this 2 and distribute it through the expression it's multiplying by. So we've got 2x, then 2 times negative 4 is negative 8. So now we've got the new equation, 5x minus 12 is equal to 2x minus 8. Now step 2 is we're going to gather all x terms, in this case x because we're dealing with the variable x, on one side. So we can do this one of two ways actually. We can try and gather all the x's on the left by eliminating the 2x on the right, by subtracting 2x from both sides. We could also subtract 5x from both sides, which would eliminate x on the left-hand side of the equation and gather all the x's on the right-hand side of the equation. Either one of those works. In general, it's often easiest to gather things in a way that will leave you with positive coefficients rather than negative ones, but both ways will work perfectly well. So in this case, I'm going to subtract 2x from both sides of this equation to get a new equation. 3x minus 12 equals negative 8. Now step 3, I'll gather all constant terms on the other side. It is important that once you've gathered all of your x's on one side of the equation, you need to gather all your constants on the other side. Otherwise, the last step won't work. So we want to add 12 to both sides. Now we're adding 12 here because we're trying to get rid of the negative 12 that currently sits in the left-hand side of the equation. This negative 12 plus a positive 12 will cancel out to 0, and that's exactly what we want. We could have added anything. We added 12 because that's what gets us closer to what we want. So we get 3x equals 4. We're almost there. Now we can use step 4 to divide and get x by itself. So currently, x is being multiplied by 3. The way we undo that is we divide both sides by 3. When we do that, the 3's are going to cancel on the left. We would reduce the fraction on the right if it could. In this case, it can't. And so we're left with a solution of x equals 4/3. We can have the solution set be the set containing the single element 4/3. So this strategy will actually allow you to solve any linear equation whatsoever. However, as I mentioned, it's not always the most efficient way of getting to your answer. Let's see an example where we're not going to use this exact sequence of steps, but we are going to use the ideas behind this general strategy of getting the variable x by itself. Let's look at another example. Let's look at the equation x plus 4 divided by 5 equals 3. Now, in this case, we want to get the x by itself. And we're allowed to add, subtract, multiply, or divide by anything we want in order to get us closer to that point, in order to get us closer to having x by itself. Now, we can look over here at the left-hand side of the equation and say, all right, well, what's happening to the x right now? Currently, we're taking our x, we're adding 4, and then we're taking that whole result and dividing by 5. And a lot of times what you want to do to get x by itself is sort of work backwards through that process. If you can describe what's happening to the x in a sequence of steps that way, then you can work backwards to undo all those steps and just get x by itself. So currently, we've got x, we're adding 4, and then we're taking that result and dividing by 5. So if we want to work backwards, we want to look at that last thing that we did, dividing by 5. Having the 5 in the denominator down here. And we want to say, all right, well, what's the opposite of dividing by 5? Well, the opposite of dividing by 5 is multiplying by 5. So let's try doing that. Let's try multiplying both sides by 5. Let's see what that does for us. Well, here we can actually do quite a bit. On the left here, remember that multiplying by 5 is the same as multiplying by a 5 over 1. And a lot of times we want to do that when we've got one of our factors being a fraction. We want to write the other one as a fraction too, so that they can match up as much as possible. Now here we're multiplying two fractions together. But remember that when we're multiplying two fractions together, we can simplify those fractions before we've actually multiplied. We can look for the same factor in the numerator and the denominator and reduce those and simplify those before actually going to the multiplication, which is very helpful for us. And we're actually going to use that even more here in a second when we do a later example. So, on the left here, we can see we're multiplying two fractions together. And the first fraction has a 5 in the numerator, and the second fraction has a 5 in the denominator. And whenever we see the same factor in the numerator and the denominator, we can cancel them. So we can cancel both the 5 that's being multiplied in the top and the 5 that's being multiplied in the bottom, even though they don't belong to the same fraction because the two fractions are being multiplied. So when we simplify this, we can see that the 5's cancel with each other, and so we just get a 1 on the top and a 1 on the bottom. Well, 1 times x plus 4 is just x plus 4. 1 times 1 on the bottom is just 1. Dividing by 1 doesn't change anything. And so, in fact, this whole thing simplifies down to simply x plus 4. And then the right-hand side, of course, is just 3 times 5, which is just 15. So, by thinking about what's happening to the x and how we can undo that, how we can unwrap what's happening to the x, we were able to take our original equation and turn it into something quite a bit simpler. So now we're almost at the end. We're trying to get x by itself. Right now, the only thing happening to the x is that we're adding a 4 to it. We can easily undo that by subtracting 4 from both sides, which we're always allowed to do. And so the left-hand side of this equation simplifies to just being x. The right-hand side of the equation simplifies to just being 11. And so the solution to this equation is just 11. (11) is the only value of x that you can plug into this equation to make it true. Let's see another example where we're going to use a similar technique to simplify the problem ahead of time before we actually go to solve it. Let's say we want to solve the following problem. Let's say we want to solve 1/2 x plus 5/6 equals 7/4. Well, this is a perfectly good linear equation. And in fact, it's simpler than some that we've seen because we only have a single term involving x. It's on one side of the equation. And so if we wanted to follow the same techniques that we had before, we could start by subtracting 5/6 from both sides of the equation. And this would be perfectly fine. This would get us to the answer. However, it's not the nicest thing to do. And the reason for that is because while the 5/6 will cancel over here on the left just fine, on the right, we have to do this subtraction. We have to take 7/4 minus 5/6. And while we know how to do that, we know how to subtract fractions, it makes things more complicated. It's a bit of a pain. And so what we would like to do is to solve this in a way that doesn't require us to do a lot of arithmetic involving fractions. And fortunately, our ability to multiply or divide by whatever we want will exactly get us there. So let's back up and let's try something else. A general technique, a trick that you can use to make your life easier is the following. When solving a problem involving fractions, you can always try multiplying both sides by the least common denominator of all the fractions. Now let's see how that works, and we'll see in a second why this does anything. It might look a little random to begin with, but you'll see in a second this is actually very powerful and very helpful. So in our problem, the least common denominator is going to be the least common denominator of 2, 6, and 4. Those are our four denominators in our problem, and the least common denominator of all of those is 12. So let's try taking our equation here, and let's try multiplying both sides of our equation by 12. Again, we're allowed to do this because we're allowed to multiply both sides of our equation by anything we want. And so in particular, we can choose to do 12 if we think that's going to help us. Well, let's see how that goes. So first of all, don't forget that this 12 has to distribute first, and you want to do that before doing anything else, before doing any simplification or canceling or anything. So our next step will look like 12 times 1/2 x plus 12 times 5/6 equals 7/4 times 12. And of course, each of these 12s is secretly a 12 over 1, which we'll want to go ahead and write that way. And now we can do the same thing that we did in the previous problem, where we've got fractions being multiplied, and there are going to be common factors in the numerator of one fraction and the denominator of another, which we can cancel. So in the first term, for example, we've got 12 over 1 times 1 over 2. Well, 12 and 2 have a common factor of 2, meaning that we can reduce them, we can cancel them before we even multiply. So 12 over 1 times 1 over 2 is the same as 6 over 1 times 1 over 1. We were able to cancel out the numerator and denominator of the two different fractions. We can do a similar thing in the next fraction pair. 12 over 1 times 5 over 6. Once again, the denominator of the second fraction cancels with the numerator of the first fraction and reduces. So both 12 and 6 have a factor of 6 in them, so you can reduce both of them by 6 and get a simplified fraction in each case. And finally, over on the right, we've got 7 over 4 times 12. Well, the 4 and the 12 can cancel, leaving a 1 behind in the denominator and a 3 behind in the numerator. Well, let's see what that does. Notice that in each case, the denominator of our original fraction has been canceled out completely. And the denominators of our new fractions are all just ones. We just have a whole bunch of ones in the denominators. That's what choosing the least common denominator did for us. When we multiply by the least common denominator, we're guaranteed that the denominators in our original fractions are all going to cancel completely. And that means that we can write down a new equation which is equivalent to the first one, has the same solution set, but only has integers as coefficients, not fractions. So the first fraction here becomes 6x, and then 2 over 1 times 5 over 1 is 10, and then 7 over 1 times 3 over 1 is 21. So we get 6x plus 10 equals 21. Now this is a different equation to the one that we started with, but it has the same solution set, which is what we really care about. So now we're going to solve this one via our normal methods. We can subtract 10 from both sides to get the 6x by itself, and then divide both sides by 6 to get x equals 11/6. And there's the solution to the problem. Okay, the last thing that I want to mention in this section is how we can identify when an equation gives us an identity or a contradiction. Now, what we're about to look at isn't specific to linear equations, but linear equations are the ones that we understand the most right now. So, let's look at the following. Let's look at 2 times x plus 3 minus 5 equals 2x plus 1. Let's look at this equation right here. Well, we can start using our techniques on it. We can start simplifying things down and seeing where we get. So, the first step is we'll simplify the left-hand side a bit. So we get 2x plus 6 minus 5 once we distribute that 2 through. And then we can simplify with some like terms, and we get 2x plus 1 equals 2x plus 1. Now, you've probably already seen that this is a little bit different than some of the others that we've seen before, but let's imagine we don't see the very obvious thing happening right now and just continue with our normal methods. If we wanted to continue with our standard strategy, the next thing that we would do is we'd gather all of the x's on one side of the equation. So I might subtract 2x from both sides of this equation. If I did that, then I would get 1 equals 1. Now this is a little bit different. And this, we can really see what's different about this. All my x's have gone away. And I've gotten down to an equation that just has numbers in it. Now the thing about an equation that just has numbers in it is that it's either always true or it's always false. It can't be conditional. An equation that only has numbers in it is either an identity or a contradiction, necessarily. Now, once we have an equation that looks like this, we can usually tell pretty easily which one it is. This equation is always true. Well, because 1 always equals 1. Similarly, if you'd gotten down to the point where it said something like 2 plus 2 equals 4, or 0 equals 0, something else like that, those would be examples of equations that are always true, which means that these equations would be identities. And because this equation has the same solution set as the original equation, this means that the original equation is an identity, meaning that it's always true. No matter what value of x you plug into the original equation, you will get a true statement out of it. So, this is how we recognize when an equation that we started with is actually an identity. It's when we reduce it to an equation which is always true. On the other hand, let's look at something like 6x plus 5 equals 3 times 2x plus 1. If we try doing the same thing with this, try to solve this equation, we get 6x plus 5 is equal to 6x plus 3. We could subtract 6x from both sides. And when we do that, we would get just 5 equals 3. Now, the thing about the equation 5 equals 3 is that it's false. It's always false, no matter what. So this is always false, which means that the equation we're looking at is a contradiction. So that means the original equation is a contradiction. In particular, that means that it has no solution. So, as I say, this is not specific to linear equations. If you're working with any equation and it reduces down to something like 5 equals 3, well, that equation just wasn't true to begin with. And similarly, if you get down to something like 1 equals 1, or some other always true statement, well, then you've got an equation which is always true.